Hello everyone. Today I will introduce the memory system and discuss how to utilize its various components effectively. This presentation is divided into 7 parts, which are overview, ROM, RAM, cache, external flash, PSRAM and Efuse. The address bus of ARM Cortex-M series are 32-bit, providing an addressable space of 4 GB. All internal and external storage or peripheral units must be operated through their corresponding addresses. Different chips have varying types, quantities, and address spaces for peripherals. To facilitate more convenient management of different chip designs by the core, the ARM core provides a predefined memory map, as shown in the figure below. First, let's examine the code area, which is designated for storing program code, though it can also store data. This section is designed to ensure efficient program execution. Next is the SRAM, which serves as an execution area primarily for data, but code can also reside here. Access to SRAM is very fast, making it essential for the smooth operation of programs. Following that are the peripherals. This section of memory primarily supports the operation of on-chip peripherals. Interactions with hardware frequently occur here. Lastly, external RAM is a section where program code and data can be stored. It typically has a large capacity, making it suitable for storing substantial amounts of data. Furthermore, there is the external device area, which primarily supports off-chip peripheral devices that may require additional storage and processing capabilities. Finally, there is the system section, which includes multiple components such as the nested vectored interrupt controller, system timer, and system control module, among others. This system section ensures the coordinated operation of the entire memory structure. In the diagram, we can see the specific allocation of memory, with detailed address ranges for code, SRAM, peripherals, and other storage. Through this clear structural allocation, we can efficiently manage and optimize system performance. The memory system primarily consists of ROM, RAM, cache, flash, and Efuse. Additionally, PSRAM is used in some IC models. The diagram presents the basic layout of the memory system, using the RTL8752H as an example. Next, we will introduce the ROM. The most notable feature of ROM is its read-only access. The size of ROM varies across different integrated circuits, but the starting address space is always 0. This address is the default location where many programs and devices begin their power-on sequence. ROM primarily contains the bootloader, flash driver, and other platform-specific features. Additionally, ROM provides certain modules for applications, such as the flash driver. Using the RTL87X2G SDK as an example, the RTL87X2G exports some interfaces through the ROM library and also provides header files for the ROM modules. Developers can access the built-in ROM functions using the ROM library or by including these header files. This approach helps reduce the size of the application code and the required RAM. Next, we will introduce the RAM. RAM is generally divided into 3 categories: TCM, data SRAM, and buffer RAM. TCM is present only in certain models of ICs and is a high-performance memory architecture used in ARM processors. It focuses on providing low latency, high bandwidth, and deterministic access features, and it includes ITCM and DTCM. ITCM is mainly used to store program instructions, allowing the CPU to access and execute the code at extreme speed, thereby providing operational efficiency. DTCM is a type of TCM dedicated to storing data, enhancing access speed to this data and thus improving application performance. Data RAM is used for storing data, executing code, and heap memory allocation, providing flexible storage options and supporting a variety of application scenarios. Buffer SRAM is used for BT-MAC and DMA transfers, and the remaining space is then used as a general heap. During the development process, RAM is generally divided into different sections based on their functions. Taking the RTL8752H as an example, the data RAM is divided into 6 parts according to their roles, as illustrated. Each section has a fixed layout order and specific purposes. ROM data is exclusively used for all global and static variables in ROM code, which form the foundational elements for system initialization and runtime, ensuring stable firmware operation. Main stack stores the stack for boot code and interrupt service routines, providing essential support for the system startup process and exception handling. Patch RAM holds global variables and RAM code for patches. Upper stack RAM is dedicated to storing variables and RAM code for the upper stack, ensuring smooth communication protocol execution. App RAM offers memory support for user applications, guaranteeing efficient operation. Data RAM heap enhances memory resource management efficiency and accommodates dynamic requirements for complex programs. Buffer SRAM is divided into different sections based on their functions. Similarly, in integrated circuits with TCM, the TCM will be partitioned accordingly. To view the specific layout, you can check the memory config file in your project or refer to the online documentation for the corresponding integrated circuit. As mentioned earlier, developers can adjust the size of certain RAM parameters in memory config header file. To help developers better tailor these parameters to their local applications, this page explains how to profile the RAM usage of an application. The RAM consumption of an application primarily consists of 2 parts: dynamically allocated memory from the heap during runtime and static RAM usage determined after compilation. The heap usage can be retrieved by calling OS memory peak, while the static RAM usage is obtained by analyzing the map file generated during compilation. The map file provides detailed information such as the starting address, usage, and maximum size of each memory segment, which helps optimize code and memory layout. The next section introduces cache. Cache is a temporary storage area designed to accelerate data access and enhance system performance. Caches are divided into multiple levels, such as L1 cache and L2 cache. The L1 cache is the fastest and is integrated directly into the processor core. It is typically split into 2 parts, the L1 instruction cache and the L1 data cache. These caches are small in size but extremely fast, storing frequently accessed instructions and data. In ARM Cortex-M series processors, not all models include separate I-cache and D-cache. L1 caches are typically found in Cortex-M7, Cortex-M55, and Cortex-M33 models. L2 cache acts as a secondary level of high-speed cache, situated between the CPU and main memory. It has a larger capacity than the L1 cache but operates at a slightly slower speed. In our BLE SoC, the RTL87X2G series incorporates L1 cache, while other series only include L2 cache. The default policy for the L1 cache marks flash memory as cacheable, while data SRAM and buffer SRAM are non-cacheable. The L2 cache has a dedicated address space and can be configured to serve as data RAM. For instance, in the RTL8752H, the L2 cache totals 8 kilobytes and can be flexibly allocated as data RAM to store data or execute code. This adaptable L2 cache configuration allows developers to optimize memory usage according to application requirements. The next section introduces NOR flash. For NOR flash, operating within its specified voltage range is crucial. Based on their voltage ranges, NOR flash are typically categorized into common voltage, low voltage, and wide voltage types. Operating outside the specified voltage range may lead to issues such as data loss or system reboots. Please refer to our approved vendor list for flash to confirm the operating range of each product. There are 3 main power modes of NOR flash: working mode, standby mode, and power down mode. The power consumption is about 10 mA in working mode, about 10 microamps in standby mode, and the lowest power consumption is less than 1 microamp in power down mode. In NOR flash architecture, the memory is typically organized using 3 main concepts: page, sector, and block. A page is 256 bytes, a sector consists of 16 pages, and a block consists of 16 sectors. We provide interfaces for flash read, write, and erase operations, and developers can refer to the relevant online documentation for detailed usage. NOR flash supports sector erase, block erase, and chip erase. Therefore, the smallest erase operation unit is 4 kilobytes. After an erase operation, the erased area will be fully restored to 1. Only an erase operation can change flash from 0 to 1, while a write operation can only change flash from 1 to 0. Typically, flash supports at least 100,000 program and erase cycles. As the number of cycles increases, the erase time of the flash also increases. The erase time is also related to the erase size of the flash. Similar to RAM partitioning, the flash is divided into different regions based on different images. The overall flash layout of the RTL8752H is shown in the diagram, consisting of reserved, OEM header, OTA bank 0, OTA bank 1, FTL, OTA temp, and app-defined section. The OEM header is used to store configuration information and user-defined flash layouts, ensuring the correct configuration is loaded at system startup and supporting flexible device initialization. OTA Bank 0 is used for storing data and executable code, and it is internally divided into several smaller sections, which will be introduced on the next page. OTA Bank 1 has the same function as Bank 0, and its size must be the same as Bank 0 to facilitate seamless switching during OTA updates, enhancing security and reliability in the firmware upgrade process. FTL is a software abstraction layer on flash that extends lifespan and improves storage efficiency by reducing frequent flash erase operations. When bank switching is not supported, the OTA temp area is used for OTA upgrades. Developers can freely utilize the remaining area according to specific application needs. The layout and description of the OTA bank are shown in the diagram. The OTA header records the OTA version, and the address and size of the corresponding sections. The secure bootloader performs security checks on the code during the startup process, serving as a crucial defense to ensure the code running at system startup is safe and untampered. The platform patch is used to extend functions in the ROM platform, allowing for the addition or correction of function features through this mechanism. The stack patch is used to extend the Bluetooth protocol stack functions in the ROM. The upper stack contains the code implementing the HCI and above Bluetooth protocol stack, making it one of the core modules for the device's Bluetooth communication functionality. The app section is primarily where the developer's application code resides, allowing developers to load and execute specific application functions to meet diverse application requirements. App data 1 to 6 are application data that need to be updated via OTA. Splitting application data into multiple blocks helps provide greater flexibility during updates or adjustments. Flash layout settings are divided into 2 levels, the high-level flash map and the OTA bank map. The high-level flash map is determined by the OEM header. Developers can load custom flash layout files through the config set option in the MP tool to generate a config file. The OTA bank map is determined by the OTA header file. For developer convenience, Realtek provides the Flash Map Generate tool to generate flash layout files. NOR flash supports different bit modes. In addition to the standard SPI interface, most flash memories also support high-performance dual and quad-bit mode SPI. In single-bit mode, the data pins used are SI and SO. In dual-bit mode, both SI and SO become bidirectional input and output pins. In quad-bit mode, SI, SO, write protect, and hold all function as bidirectional input and output pins. By default, the flash typically boots up in the stable 1-bit mode. Users need to call specific interfaces in the app to switch between different bit modes. The ability to switch to quad-bit mode is related to the flash model. To support new flash models, please confirm with Realtek. NOR Flash provides a flexible block protection mechanism to prevent accidental erase and write operations. The number of protected blocks is typically determined by configuring the BP bits in the flash status register. It is important to note that we only support block protection operations starting from the low address. As shown in the right diagram, the BP4 bit in the status register can be used to identify the direction of locking and is set to 1 by default. In addition to the evenly distributed block protection layout shown on the previous page, there also exists an unevenly distributed layout, typically found in small capacity memories. Currently, for this category, if locking to 1/2 is possible, we supports full lock, no lock, and lock 1/2 these 3 locking options. Other levels are not supported. If locking to 1/2 is not possible, only full lock and no lock are supported. If read or write failures occur during usage, we should check the following. Check BP level. The locked area cannot be erased or written to. Check write protect pin, which prevents accidental overwriting of the status register to ensure data integrity. Check flash supply voltage stability. Flash not under operation voltage may cause data loss and restart. Check software flow, such as whether the flash nor try high-speed_mode function is called for calibration when altering the flash operating frequency. Check relevant data pins for connectivity or signal integrity issues. The next section introduces PSRAM. Compared to SRAM, PSRAM is slightly slower but offers lower cost and power consumption. Compared to flash, PSRAM is faster but lacks non-volatility. PSRAM is suitable for scenarios requiring relatively high-speed storage. In terms of read and write operations, PSRAM is simpler. It can be accessed directly via addresses, similar to RAM operations, highlighting its ease of use. PSRAM serves 2 primary purposes. First, it acts as a buffer to improve screen refresh efficiency. By preloading image data into PSRAM, screen display latency is reduced, enabling smoother and faster refresh rates. This method is particularly well suited for display applications requiring high dynamic effects. Second, PSRAM can store and execute code. Critical functions or global variables can be directly allocated to PSRAM, ensuring rapid execution for performance-sensitive code segments. This also reduces reliance on flash memory, freeing it for other tasks. Developers can utilize macros defined in app section header file to place specific functions for execution in PSRAM, or they can modify the scatter file to allocate a certain object file to the PSRAM section, thereby executing functions from a specific source file in PSRAM collectively. The power consumption modes of PSRAM can primarily be divided into deep power down mode and hybrid sleep mode. In DPD mode, when the system enters DLPS, all contents in the PSRAM will be lost. This mode is ideal for applications where long-term data retention is not necessary, as it minimizes power consumption. In hybrid sleep mode, developers have the option to retain certain parts of the PSRAM, although this will relatively increase power consumption. Here, we provide some power consumption data for the hybrid sleep mode, allowing developers to better balance data retention and energy consumption in their application design, thus achieving the optimal balance between performance and energy saving. The next section introduces Efuse. Efuse is a block of one-time programming memory which is used to storage the important and fixed information, such as UUID, security key and other one-time programming configuration. The single bit of Efuse cannot be changed from 0 to 1, and there is no erase operation to Efuse, so be careful to update Efuse. We also provide the MP tool to update certain Efuse sections. Thank you.